I do this. Yes. Okay. Sorry. And now? No. Can you hear us? Yes. Sorry. So as I told you that from recent studies, we know that there is AGN and host galaxy connection, which usually suggested by different tests. So in my work, I will focus more about how the black hole accretion rate and star formation rate of host galaxy correlated. We know very well that because they very well studied for high redshift universe, actually relatively high redshift universe, because with the James Webb Space Telescope, we know that high redshift now it's like 10, 11, but in this case, it's a high redshift, meaning like redshift 6 or 8. And we know that shape for them is quite similar. They are slowly going from the early universe up to redshift 2, 3, and peak at that redshift. And then they rapidly decline to the local universe. What? Going on. So here's the question, what's going on with the local universe? Because in local universe, what we know that we have, first of all, weak AGN population. We can just probe it because it's easy, it's local universe. And then in the local universe, we also have the galaxies with a quenched or very weak star formation rate, so ellipticals mostly, so we can probe it. And unfortunately, we not probed it very well. So my study will be absolutely focused on the low redshift universe. So what we do? To retrieve the host galaxy properties, we are using the optical galaxy sample from SDS-SDR8. It's very famous Gauss catalog, which have the star formation rate and stellar masses, spectroscopical star formation rate, stellar masses for more than 700,000 galaxies. Redshift is local one, almost local one. It's less than 0.33. And if we plot the star formation rate versus stellar mass diagram for this sample, we see the very familiar shape. And if we started to distinguish the galaxies on this diagram, star formation rate versus stellar mass, we have usually two populations, in general, two populations. So on the top, Yes. So on the top, we have the very famous main sequence of star-forming galaxy, where it's located mostly star-forming galaxy, which the process of formation of stars is in very active phase. The population of stars is mainly young there, and the morphology mostly spiral or irregular one. And when we go down, we have the quiescent galaxy population. Usually, the star formation processes in such galaxies, they are quenched, very weak. They have very old stellar population. They're usually red in color, and morphology mainly elliptical one. So the question, where is the AGN? So to probe the AGN in these galaxies, we are using the X-ray because it's the easiest option. So we combine two samples. We combine the sample from XMM-Newton Serendipitous Catalog and from Chandra Source Catalog. So in common between all these two catalogs, we have 170 different sources. So we can cross-calibrate our sample. So the cross-calibration was quite simple. We just changed the energy range to fill each other because Chandra and XMM hard band, they have different range. And then we just cross-calibrate for some systematic difference between X-ray observation. So as you see, when we just calibrated XMM toward the Chandra and plot them versus Chandra and calibrated, we have quite fluxes. We have quite one-to-one. Some scatter could be probably due to intrinsic variability of these sources because it's AGNs. So again, I will not stop too much in detail about this cross-calibration. We can just discuss it later because I have limited time. So another step which we should remember that when we are using the archival data, X-ray archival data, there is a probability that there is some host galaxy contribution because we have star formation in these galaxies. So to correct it, we are using the scaling relation between X-ray luminosity and star formation rate for two different types of galaxy population. So in our case, for star-forming galaxies, we're using the scaling relation between X-ray luminosity and star formation rate from Lumiere. So what we are doing, we just taking the star formation rate of host galaxy and like rescaling to understand which X-ray luminosity should host galaxy provide if it has such star formation rate. And then this X-ray luminosity from star formation just subtracted from our total X-ray luminosity, which we have from archive. The same is a quite similar one. So in this graph, you see the just distribution of X-ray total luminosity versus redshift, where by bars, I'm showing how much of X-ray luminosity from star formation was extracted from our total one. So in most cases for our sample, we are not extracting too much. So the effect of host galaxy is quite small one. And the same was did for quiescent one, but in case of quiescent one, we are using absolutely another scaling relation because population of X-ray emitters in quiescent galaxy or elliptical galaxies, they are quite different from star-forming galaxies. In star-forming galaxies, we usually have like two population of X-ray binaries, while in elliptical, we usually have like just low mass X-ray binaries. And then we have like a fraction of hot gas, which could also emit in X-ray. So it's the same, but the approach is the same, but we're just using the another scaling relation between X-ray luminosity and K-band luminosity for three different sources of possible X-ray emission. So the idea is the same. We have total X-ray luminosity from which we extracted the predicted X-ray luminosity from three different sources from host galaxy. Another thing which we should take into account that we are using SDSS sample, so it means that it's magnitude limited. And in our case, when you are plotting the distribution of stellar masses versus redshift for two different host type galaxy population, you see that we are missing some part of quiescent one. It's just because the quiescent ones, they have different mass to light ratio for the stellar population. So it means that quiescent galaxies with the same mass as star forming, they are less bright. So it means that at some point, at some edge of your limit for SDSS, they just part of your quiescent galaxies, they just drop out. So to fit it, we just, to fix this problem, just to take into account, we are providing like the sensitivity limit for our sample. So we just calculated using the mass to light ratio evolution for the most old stellar population using the Brussels and Charlotte 2003 and Krupa 2001 initial mass function. And this is the great light, the line. So we use the limit of our SDSS sample. And as we see that actually it's not working very well, but it's the problem that in this plot, we are having not the entire SDSS sample, we just having that part of sample which having X-ray counterparts. So it means that some of elliptical just disappear from this range by some reason, so they just disappear. So just to avoid including incompleteness our sample, we just cut it the lower part of our stellar mass distribution with redshift. It just a bit higher, like for 0.2 dex up, and at this everything what with mass stellar mass less than 10. Just to avoid comparing star forming without quiescent. So, because just we have low fraction quiescent galaxies in these ranges. So, and as a result, we have almost 2,000 objects, and they almost have to have star forming and quiescent. So for each of these source, we just use the X-ray luminosity in hard band to calculate the specific, so-called specific black hole accretion rate, Why it's specific? Because for our object, we don't have black hole masses, and the only option to retrieve the black hole masses is to use in some kind of scaling relation. In our case, we are using just the stellar to black hole mass scaling relation, which is quite familiar one, and calculating the black hole accretion rate for all these sources. So the next things, the first idea of our work was to recreate the black hole probability distribution in the local universe. To do this, we need to take into account that X-ray observation, their sensitivity is quite different depending on the exposure time and of axis and other stuff. So we need to correct the number of our sources using the different sensitivities for our stuff. So what we did, we just found out how many SDSS galaxies is falling inside of area of observation of XMM and Chandra. And for each position of this galaxy, we just calculated the flux upper limit or retrieved flux upper limit. So now we know how many. So we have 2,000 detections, but we know that in reality, the 32,000 galaxies should be observed by Chandra or XMM, but they did not because there is no homogeneous sensitivity of the observation. So using this flux upper limit for two surveys, we just calculated the cumulative distribution to flux upper limit. So we have like for different cameras in XMM and for different detections in Chandra. And on the next slide, I will show you how we use it. So to retrieve the probability density function for black hole accretion rate in the local universe, we did it actually in two ways. The first one, we just collected the object in some certain bin of black hole accretion rate. And then we just use it our cumulative course, which is where we have a flux upper limits, and we can convert it to black hole accretion rate using this, the redshift of the host galaxy and mass of the host galaxy, and just to multiply it, like correct it for how many sources in general should this given black hole accretion rate should be observed. And in such way, you just correcting the all galaxies, all objects which you have, and then combine them together to obtain the probability density function. The second one method is a bit more difficult, not just more complex, to obtain the continuous shape of black hole distribution, not just histogram, but continuous shape. You just assuming that the likelihood of detecting, of observing the black hole accretion rate at a given point, it's a normal distribution, where you're just assuming the width of your distribution, like errors of your flux, X-ray flux. Then you again just correct it using the cumulative curves. And then each object, when you obtain, you just sum up and obtain the probability density function. So result is like this one. So we obtain it for 4 different masses. So you have 4 different stellar masses. And then we just probe it for all galaxies in our sample, and then separately for star-forming and quiescent galaxies. So the main result which we can obtain from this graph is that in local universe, the accretion is very low efficient. So the peak of our probability distribution is near -4. So it's very low efficient accreting black holes. And if you're comparing the star-forming galaxies with the quiescent one, you can probably see that star-forming galaxies peaking a bit higher, so they are a bit more efficient than quiescent one. So black holes in star-forming, they are a bit efficient than quiescent one. Also, if you're comparing this one to the results obtained from literature, from other studies, you see the shapes that almost identical, but we are missing the part at the highest accretion rates. It's just a problem of our sample, first of all, because the SDSS sample was just compiled without very bright AGM, so there is no quasars in our sample, so we're just missing them. But due to evolution, we know that there are not too many of them in the local universe. So there's also an interesting fact here that at some point the distribution, the probability distribution of black hole accretion rate started to flatten or going down. So it can be due to the fact that in local universe, when you are using such big object, you are able probably to trace the physical limit at which you are still able to register like relatively efficient X-ray agent. So we still don't know if this is for sure turnover, because it's very difficult to probe here because we have a sensitivity limit of our observations here. But as a preliminary result, it's like this one. Using these probability distributions, we can actually calculate the fraction of AGN in the local universe. So at the first attempt, we decided to calculate like the entire AGN fraction. So in our case, we just taken the limit at black hole accretion rate near -5, because we have sensitivity problems at this side. And then if you looking at the fraction of AGN in different masses, you see that the fraction of AGN in the local universe is from like 7% up to 47%, depending on stellar mass. And if you're calculating the fraction of bright AGN, which is accreting near 1% of Eddington limit, we will see that the fraction is less than 1% compared to the total population. So we don't have that much. Also, if you are looking just in numbers, you see that actually the fraction of bright AGN in the quiescent galaxies usually significantly lower than in star forming. And if you also calculate the average number of black hole accretion rate in the local universe, you also see that actually supermassive black holes in quiescent galaxies, they accreted slower compared to star forming galaxies. If you're comparing with the stellar masses, you usually don't see too many results, but there is a quite weak increase of AGN fraction of bright agents if you are going from lowest mass to highest mass for star-forming galaxies. And when you are detecting also the same increase in fraction of entire fraction of AGN from the lowest mass to the highest mass for quiescent galaxies. So when the second goal of our work was like, can we look if there is dependence between how fast black hole accreting depending on the star forming rate and stellar mass of our host galaxy. So for this case, we just plotted the star formation rate versus stellar mass diagram as is beginning. But instead, in each bin, it's like 0.25 index bin, we are calculating the median value of X-ray luminosity of agents falling inside this bin, or black hole accretion rate, or the median black hole accretion rate. So in this way, we can see again that in local universe, we have mostly low to moderate luminosity agent, and accretion is also low efficient one. If we comparing looking for the correlation with the properties of host galaxies, we see that X-ray together, X-ray for both for star-forming galaxy on the top and for quiescent one, it's increasing with stellar mass. So if you go in this direction, oh, sorry. So, okay. So, but in case of black hole accretion rate, we don't see this one. So we don't have increase with the stellar mass, but instead we have slight decrease with the stellar mass for quiescent one. But for sure, we see that population of quiescent one galaxies, they have lower, in average, lower X-ray luminosity compared to the star-forming one, and the same trend for black hole accretion rate. So we decided to check it. So we plotted the black hole accretion rate versus star formation rate diagram for 4 different stellar mass plots. And as we see that there is an increase from quiescent one to stellar one, and statistically significant, we have only this mass bin and this one. For that one, for this one is the highest one, we have just flattering. And it's strange because flattering, at some point we see even the drop here. So we just decided to check why we have this drop and why we have flattering, because it can be due to some selection effect or for evolution. And if we are going back to our stellar mass diagram, we see that at some point we are missing some object at some lower redshift or higher redshift. And also this, as we know, very fast decline in black hole accretion rates with the redshift. So we decided to divide this, our sample for 2 redshift samples and to check if we have, if we have the same flattering. And now, as you see, we have the flattering of black hole accretion rate with a stellar mass for each redshift bin and for each stellar masses. And if you plot just cutting the last dots here, you see that we have now the statistically significant increase of black hole accretion rate with a stellar mass for all 4 stellar mass ranges. So here we also plotted the position of main sequence of star-forming galaxy, because it seems that it's coinciding position with the position of our drop. But again, it should be not like a prominent result. It's not a physical reason. And also, I will move here. We decided to avoid the uncertainties of stellar mass to black hole mass ratio, which we are using in our black hole accretion rate conversion. And we calculated mass independent parameter, which is absolute black hole accretion rate in this one. And we still here see that increase for quiescent, we still have significant increase for quiescent galaxies. But when we have, then we have the like flattering for star-forming galaxies. And if we are comparing the same our diagram with a similar one in the literature, but for different parameters, for example, for the redshift, we have only one work which is probing the same redshift, almost the same redshift range. We have this deviation probably because the sample which was used have significantly lower stellar masses. And when we are going to higher redshift, we are seeing that actually our relation is much flatter comparing to the higher redshifts. But the problem is that they are mainly star-forming galaxies. So we are comparing like we are comparing quiescent plus star-forming, while they have like just star-forming galaxies. So another stuff, if you're using the different galaxies types, because in, for example, there is a work about bulge-dominated galaxy, their relation even for higher redshift is much flatter as ours, but at the same time they are probing the higher redshift. So it means that slope is not always dependent on just redshift evolution. It can be also dependent on the host galaxy properties. And also another stuff, as I told you, our samples is lacking the type 1 AGN. So if we are studying the same relation for type 1 or type 1 plus type 2, we are again seeing that the relation is going steeper. So it means that at some point, it's quite difficult to understand if our slope is evolution or it's just dependent because we are not including type 1 AGN, or just because we are using quiescent galaxies, which is going steeper. So another stuff, the last one, sorry for... So the last one stuff is like about this one. So in our case, when we're comparing the black hole accretion rate with star formation rate, we are not knowing who is dependent on whom, because it can be that black hole accretion rate dependent on star forming or star formation rate, or star formation rate on the black hole accretion rate. But in general, probably neither of them dependent of each other. They probably dependent on some other physical parameter which is available for our host galaxy. And usually we are suggesting that both black hole accretion and mass accretion into stars dependent of amount of gas which is available in our host galaxy. In our case, we don't have, unfortunately, the masses for gas component inside of our galaxy, but we have the stellar masses, so it means that mass which was the mass of gas which was converted to the stars. So when you are plotting the ratio between black hole accretion rate to star forming rate, just for star forming galaxies, because we assume that we know that star forming galaxies evolving with a stellar mass, so they have this main sequence of galaxy, you see that more massive system, they are just more efficient in feeding the central black holes rather than forming star for sure. It can be due to different reasons. We don't know why. So it can be due to different amount of gas in the high massive galaxies, or it maybe can be due to the fact that more massive galaxies, they have denser core inside, or it can be also due to the fact that lower mass galaxies, they usually have like star forming feedback or a supernova explosion, which can reduce the amount of gas available for accretion of the black hole. And also we are seeing that with the redshift, because we are comparing our result with different results in the literature for different redshift, we see that there is no difference, no evolution with the redshift. So it seems that black hole accretion and so star formation rate accretion, they are coherently evolving with the redshift. So they have this the similar ratio, but at the same time, they are not dependent of each other. They are dependent probably of a gas amount in the galaxy. So I will leave my conclusions here. Thank you for attention. Sorry for delay. I'm waiting for your questions.
Thank you very much. So, any questions from the room?
So usually people find a strong relation with stellar mass rather than star formation rate.
Yes.
Like, so everything like the specific accretion rate, stellar mass controlling for the star formation rate. Maybe for the.
So we don't know actually, because everything depending on which type of sample you probing, on which galaxies you're probing. For example, when we did the previous work on the just using the XMM data, when we're looking at this diagram, we saw that actually for star forming galaxies, the accretion rate is evolving with the stellar mass too. But when we included the Chandra sources and when we just removed the incompleteness in star formation in stellar masses, we just lose it. So it's quite challenging because we don't know. Maybe usually when we are looking at the literature and see that black hole accretion rate is evolving with stellar mass, sample is usually limited to really high luminous agents. And that's why it can be the problem. And in our case, we don't have really high luminous agents. So if, for example, we will include them, probably we will find the same relation with the stellar mass. But at this point, we don't see.
Yeah, I think also even in that you found that was stronger in star formation rate.
Yeah.
There is a question from the chat. So very interesting results. Is there any chance that in massive systems, the presence of a relative massive supermassive black hole is decreasing the star formation rate?
Yes, probably yes, but I actually don't know if it's true or not, because it probably is that when you have a really massive galaxy and you have the AGN feedback, it can be like self-regulation. But again, it's a matter of AGN feedback, and we need to check it. In our case, it's very difficult to trace because we don't have black hole masses. We don't know. We just assume that black hole mass is scaling with star formation with the stellar mass. So yes, when you look at that diagram, you usually see that, yes, the most massive one, like assuming the most massive one, but in reality, you need to check with the real mass of black hole. So yes, the AGN feedback can affect this one, can regulate this one, but in this study, we cannot check it, unfortunately.
Any other question from the chat? No? So if Everyone is happy, then let's thank